we're going to look at a variant of the longest common subsequence problem. This is called the edit distance. Maybe you guys have seen this before. The idea is you're given two strings and you're asked how similar are they, except that here you're not just looking at the common characters or the longest common subsequence. When you have a match, so the way you write this down is you write this down like an alignment, where you write one string below the other, and you're allowed. So for instance, let's say those are your two words. You could have things that, of course, it's perfect if they are the same when you write it one below the other, but it's okay to put gaps in one of the sequences or in both sequences at different times in order to make things aligned, and it's okay to have some mismatches. Thank you. So let's see. So for instance, is there a mismatch somewhere? Yeah. So for instance, in the first example, in the second example, the A and the E don't match, but you allow it, but with a penalty.
So is this like the reverse LCS?
It's not quite the reverse LCS. In fact, it's a very general LCS, because it says that, so in LCS, you just don't allow mismatches, right? Here you're saying some mismatches are better than others. Hey, hi. So just to get him up to speed, we're looking at something called the edit distance problem. We're given two strings, and our goal is to write them write them one below the other in such a way that you get the best match. Typically, you want to think of this as an edit distance problem. Think of how Word might try to figure out if you mistyped a word, something, right? So you are trying to type occurrence, and of course, let's say you don't know the spelling. You make up some spelling, and that's what it looks like. Now it needs to figure out that, oh yeah, maybe you were trying to say occurrence. And so so this tells you how it would try to figure that out. Of course, it knows that people make a mistake with A and E, for instance, or with the number of N's or the number of R's. But if instead of the A, if you had a Z, then it would say, oh yeah, that's not a very good match. So mismatches are not always the same. Some mismatches are worse than the others. So you have a very clear cost for the mismatch. In this case, in this simple example, the mismatches are all the same cost. But in general, I can make this much harder by saying different mismatches have different costs. Okay? So you can either have a mismatch or you can have a gap, which is the same as saying you can either have a substitution or you can have an insert or you can have a delete. So that's why it's called the edit distance, because you're asking, how do I edit that first string in order to get the second string? And if, let's say, this is your answer, then it says, in the first string, put in a gap character after the second one, put in a gap character after the fifth one, and then delete that A. Okay, so that's really what it says. If you had used that one there, it would say put a gap character after the second one and replace the A with the E in the sixth position. So that's the editing that you're doing in order to get from string A to string B. And you want the edit that has the least cost. Every edit job has a cost. Some have higher cost than others. You want the one with the least cost. That's the general setting for this problem. Yeah? Clear? So you said some of you have seen this, but still let me try and set up the thing in a general manner. Applications, the Unix diff. How many of you use Unix systems? Yeah, Linux, okay, good. So if you use the diff command on Unix, it uses this algorithm that we're going to describe. And then there are problems in speech recognition and computational biology where this is standard stuff. The reason in computational biology you have DNA sequences and you want to know how different some DNA sequences are. So in each of those problems, the way you set up the gap penalty and the mismatch penalty are very different. And so you want to do this in the most general way possible. In general, it says that once you've decided on a certain alignment, on a certain way of writing things down, then this is how you measure the cost. You add up all the gaps in the first sequence, you add up all the gaps in the second sequence, and then you add up all the cost of the mismatches. All right, so you take the first sequence, you write down the second sequence below it, you count all the gaps. Here they're all said to be of the same cost, but the mismatches, you can make them a general cost or you can make them a same cost. So problem changes depending on how you pick those numbers there. And again, in some cases, for instance, in computational biology, often the mismatch costs can be very different depending on what it is that you're mismatching. And the gap costs can be different based on whether it's the first. So there's a difference between something called the gap opening and the gap extension. So for a single gap character, there's a certain cost. But if you have a gap of 7 characters, then there's only a cost for the first one. The other ones are a lot less. So it gets very complicated in some of these applications. And so what we need is something fairly general so that we can deal with any of these situations, right? All right, so let's see how this goes. The general strategy is very, very similar to what we did for the longest common subsequence. We're going to set up a two-dimensional matrix. We're going to put one of the sequences along the rows, one of the sequences along the column, and then we're going to write down a recurrence relation. So here is the recurrence relation that we are going to need. Before we go to the recurrence relation, it's a good idea to think about what the logic is behind the recurrence relation. So the logic is actually quite simple. If you just want to think about, so let's say we take that example there. If those are your two strings, we start at the right end and say either the last two characters are aligned, are sitting right below each other, or they're not. If they are sitting right below each other, there are two possibilities. If they are the same, it's a match. If they are different, it's a mismatch, and there's a cost associated with it for each of these cases. If they're not sitting one below the other, then there are two possibilities. Either you have a gap here or you have a gap here, right? So those are your 4 possibilities. And for each of these, we write down the cost and reduce the problem to something smaller. That's the general strategy that we did with the longest common subsequence. And that's exactly what we're going to do here. Fine? Okay. So here is in the end, so I'm taking liberties with you guys and jumping straight to the recurrence relation. So here is the recurrence relation. So this recurrence relation says, in case 1, It's looking at the first I characters of X and the first J characters of Y. And it's saying, okay, what's the best way to align them? Align them simply means writing them one below the other and figuring out which characters fall one below the other, right? That's what an alignment is. This much is clear to everyone? So the first string has I characters, the second string has J characters. And so there are three possibilities as it says here. Either the last character xi and yj are one below the other, or they're not. So case one is when the ith character of x is below the jth character of y. If that happens, there are two possibilities. Either it's a mismatch or it's a match. So whatever is the mismatch cost, that's what we pay for it. Of course, if they're the same, the mismatch cost may be 0, but that's fine. Okay. So that's the mismatch cost plus it's the cost of aligning the remainder of the two strings. So that's I minus 1 and j minus 1. So you remove that last character from both and try to align the rest. That's your recursive call, right? Otherwise, you'll either leave a gap in the first guy or a gap in the second guy. If you leave a gap in the first guy, you're discarding a character from the second sequence. If you're leaving a gap in the second guy, you're discarding a character from the first sequence. So that gives you either xi minus 1 and yj or xi and yj minus 1. These are your two possibilities, right? So if you recall what we did in LCS, it's something very similar, except that we made things more complex for the mismatch part. So other questions? Are you comfortable with what we've said here, or was this too fast?
I understand it. How different can the two strings be at the beginning?
They can be completely different. It doesn't matter.
Would this algorithm just turn the second string into the first string in that case?
Exactly. So it's going to try and find the best way to convert that string into this string. And based on your mismatch costs, it'll try to match them appropriately. Otherwise, it'll simply say, okay, let's put a gap for every character here and put them completely apart. So it just depends on what those individual costs are, and it'll give you a certain result. Fine? So in the end, you get this is the code that simply says if you're given m and n, which are the lengths of the two strings, and the two strings, that's x1, x2, xm, y1, y2, yn, then there are two other parameters, delta and alpha. Delta is the gap cost, and alpha is the mismatch cost. That's it. So we initialize, we make the first row and the first column. So here it's interesting. If in the longest common subsequence, if one of the strings was empty, there was no cost because there's nothing in common. So you would write a 0. Here that's not the case, because if one of them is empty, you would have to put gaps in order to match things, and so every gap costs you. And so therefore, the first row and the first, that's the first row, and this is the first column. You're multiplying, you're figuring out how many gaps you're going to need in order to match them, right? So you get j times I times delta and j times delta. That's your first row and first column. So things start off differently as well. And then the rest is exactly the coding of your recurrence relation. All right? So what do we have here? For I equals 1 to m, for j equals 1 to n, which means you're trying to fill up the table, and you're trying to fill them up row-wise. And then Mij is one of those three things. It's either a substitution cost or a gap cost. The substitution cost says match the I with the j or mismatch the I with the j, and then take the remainder and find the solution. Or you put in a gap in the first string or a gap in the second string. Yeah.
So if they match, that alpha of x, I, y, j will be 0?
Yeah.
Okay.
Yeah. Yeah. So somewhere you would have a simple procedure that says, okay, let's look at these two and figure out what those characters are, and I'll give you a cost. In this case, alpha is it looks like a table that you're given that says it doesn't matter where these characters are. If you're trying to align A with a C, this is the cost, and so on. So these are costs of any mismatch. Doesn't matter where it's located. So that's all you have, and in the end, you report the item in the last row, last column. Are we good? So this part is pretty clear. You're going to take m times n times, because that's the size of the table. And you're going to take m times n space, because that's the size of the table. Yeah?
Right. And just to make sure that I understand this, so for case 1,
Yeah.
they either match and then you pay 0, or
Right.
they do not match and you do pay a cost.
That's right. So what we're going to do is, let me see if I can quickly write this down so that it becomes clear. I would have a table. So let's say we are dealing with DNA strings. Okay? If it's DNA strings, we have A, C, G, or T. So these are all letters of my alphabet, right? In general English, you'll have A through Z. In DNA sequences, you'll only have these 4 characters, because that's what biology tells us. And this would be the alpha table. So it'll tell you that alpha of A with A is 0, C with C is 0. And here it'll give you some cost. Maybe it tells you that A with T is 1 and A with C is 2. Maybe. Right? So whatever you're told, that's what you use. So this could be a sample. Hey, what did you do to yourself? Hi. So, so that's really all there is to this problem. And once you're given this cost, remember it's not, it doesn't depend on the length of the string. It just depends on the size of the alphabet. So it tells you how the alphabet characters are related to each other. Yeah?
So then, okay, yeah, so that makes perfect sense. And then for case 2, that's saying that they didn't match, but instead of replacing it,
You're just going to leave a gap, yeah.
So you'll be inserting a gap in the y string. That's why y doesn't change, but x.
Correct. Yeah.
Okay.
Right. So for instance, if the spelling was occur, which is the right spelling, and let's say you put in let's say you put in 1 C instead of 2 C's, the way you would match it is by putting a gap here.
Okay, cool.
Right? So depending on where you put the gap, whether in the first string or the second string, you might have either case 2A or 2B. So this allows for all those possibilities to happen. It simply says, we'll pick the best. We don't care which it turns out to be. Okay? So the problem is right here. It uses theta m times n time as well as space. And there's a lot of research on how to reduce the space requirement for this algorithm. And this turns out to be way more difficult for us to talk about here. I'm not going to do that, but I'm going to tell you a little bit about this so that maybe if you're interested, you can go and read up on this. And in fact, they have some slides here, but it's simply not worth it for us to go through them. So they asked the question, remember, this is called quadratic space, right? Because we have space that's proportional to the product of the lengths of the two strings, right? And we'd like to avoid this. What we would like, ideally, is that space, theta of m plus n, not m times n. If it is m plus n, that would be linear space. If it's m times n, it would be quadratic space. If m is equal to n, the first one becomes n squared, the second one simply is order of n, right? So turns out this guy Hirschberg figured that out some gazillion years ago. And the way you figure it out is by using something called the edit distance graph. So the basic idea is, well, actually the basic idea is right here. The basic idea is you want to, when you're doing the computations, right, you can, once you've figured out this row, you're going to need that in order to figure out the next row. And then when you want to go to the third row, you can essentially forget the first row and only use the second row. That's the basic idea, but that doesn't really work, because in the end, you have to figure out all the way up. And if you've forgotten the earlier rows, it doesn't help you to, so it helps you to figure out the optimal answer with less space, but it doesn't help you to figure out the actual alignment. And that's where the rub is. And so, so it's easy to reduce the space to find the optimal answer for the length of the longest common subsequence, or for that matter, the actual edit distance. But to actually figure out the edits that you need in order to get it to work is a lot more challenging, and that's the part that I'm not going to tell you about. And it turns out it uses a combination of divide and conquer and, and dynamic programming, and it gets pretty hairy. So in particular, it says that what we want to do is to figure out the best path from 0, 0 to m comma n, because we know that's the answer we want. We know that's where we have to start, because at the start, both strings are empty. And then we need to figure out an optimal path. And that optimal path, if we do this row by row, we can eventually figure it out. But if we start to forget rows, then we don't know how to reconstruct it. So it uses, so essentially it says that if I want to force it to go through I comma j, then I can break it down into two paths, right? And then it becomes like a divide and conquer. I could break down the whole piece into two halves, solve this half, and then piece them together. So it's quite hairy. I really don't want to spend time here, but I just wanted to tell you about that. So there are about 6 slides here. They still don't really help, but you can see the divide and conquer working here. You take the halfway point, solve this half, and then try to patch them together. Yeah?
What book is this?
This is the book by Kleinberg and Tardosh.
Is it the MIT one?
No, these two guys are from Cornell, but it's not a new book. but I love the examples in here. And these are slides that were created by somebody else from, I think it was Princeton, for his classes. So I'm using his slides here. Questions? All good? So yeah, I'm sorry, we won't be able to really go through all of this. So there are two more steps here. If you do it sort of the simple divide and conquer, it becomes T of Mn is T of Mn over 2 plus O of Mn, which if you know how to solve recurrences, and that's another thing that I would have to explain to you here, you would end up with something called big O of Mn log n. And then there are some other tricks that you can use in order to get rid of the log n term and get just a big O of Mn. So it's nasty stuff. But just to give you a flavor of how much work on just this simple problem to get rid of this simple log n thing and turning the space into a linear space, how much work has been done here. Yeah? Okay. So, yeah. Right. So now we're going to look at, oh, it's already 10 o'clock. Okay. So now we're going to look at a very different problem. Again, it's not quite three-dimensional dynamic programming, but it's quite interesting. This problem is a problem from your book, from Corman, Lyserson, Rivest-Stein. And the problem I want to talk about is this one here, so I'm going to let you read this. This is the Bitonic Euclidean traveling salesperson problem. So let me show you the figure. How many of you don't know what the traveling salesperson problem is? Everyone has heard this? Traveling salesperson problem is simply a problem of visiting all the cities and getting back to the start point with the minimum amount of distance. So you're a salesperson. Your job is to visit the capitals of the 50 states, and you don't want to be traveling. You don't want to be driving too much. So how do you minimize your driving in such a way that you go visit all of them and come back? That's the traveling salesperson problem. All right? But this one is a slightly different one. It's called the Bitonic one, where you're told that, what are you told here? Where's the description of the problem? Yeah. So here we simplify the problem a little bit. We don't look at the general problem. By the way, the general traveling salesperson problem is very, very difficult. It cannot be solved efficiently. It's a famous NP hard problem, and people don't know how to solve this in polynomial time. Okay. So you should know about this term called NP hard, which simply says no man on this planet, or no woman on this planet has figured out how to solve this in polynomial time. That's what it means, roughly speaking. Okay? That doesn't mean somebody can't find it tomorrow. It's just that we don't know the answer now. It's an open question. All right? So we, instead of looking at general traveling salesperson tours, we're going to look at something called a Bitonic tour. What's a Bitonic tour? In a Bitonic tour, we start at the leftmost point, or think of it as the westernmost point, and then we will only go rightwards. So we'll only go east, and then once we hit the easternmost point, we're only going to go west. Okay? That's called a Bitonic tour. And you can see an example here. In this, let's say there are 7 points. This guy here is not a Bitonic tour, but this one is a Bitonic tour. Because you start at the leftmost point, and then you only go right. And then once you hit the rightmost point, you only go left. Is that clear? Here, you're doing some zigzag stuff. That's not acceptable. So what we're doing is we're not looking at all possible traveling salesperson plans or tours. Instead, we're only going to look at these Bitonic tours and find the best one. So the problem asks, how do I find the best Bitonic tour in a traveling salesperson problem with the additional information that all my points are points in two-dimensional space. They're all on the plane. Okay? So every point is given by coordinates, or think of it as GPS coordinates. So it turns out that greedy algorithm is not going to work for you. Okay? And you can imagine if I gave you 50 cities, you're not going to be able to do this by hand. And if I gave you 10,000 cities, you can forget it. Right? So we would like an efficient algorithm for this. And I just told you that greedy algorithm is not going to work, which means that dynamic programming is pretty much our only alternative. Okay? So remember, our first step in solving dynamic programming problems is to try and build a recursive solution, right? So like we did with the edit distance or the longest common subsequence, we play around with the last guy or the first guy and do something. So the question is, what am I going to do here? Yeah.
Definitely not be solved, but so recursively we usually start what is it, top down, which
Yeah.
go from the end and then try to go to the beginning.
Okay.
So I guess since we have to end at the point we start at,
Yeah.
that means that's also where we start our recursive algorithm.
Yeah.
And then if we're moving backwards, yeah, that means we need to go right. Yeah, right. That's the part I have to figure out.
Right. So any other thoughts before I give you some more clues? Yeah.
Does the point start out with just the points and you need to figure out
Yeah.
how to...
Correct. You're only given the points. Yeah.
And you assume that it's already a Bitonic, or do you need to figure out if it's Bitonic?
No, there is no tour, so you can't figure out whether there is anything Bitonic because there is no tour to look at. You're only asked to find the best Bitonic tour possible by anybody. So you want the optimal Bitonic tour. Does that make sense? Among all possible Bitonic tours. By the way, there are many Bitonic tours. Okay? For instance, in this particular example, I could go like so. I could go like so, like so. This is a Bitonic tour. Okay? But it may not be the best. So there are many, many Bitonic tours. Essentially, what you're trying to do is to put some of these in the westward path and some of these on the eastward path, and the remainder on the eastward path in such a way that the total distance is minimized. Yeah.
Oh, okay, I forgot about that. The cost is the Euclidean distance.
Cost is the Euclidean distance.
Okay.
That's correct. Yeah. Yeah.
Would a divide and conquer approach work here?
Divide and conquer is not a bad idea. It runs into a variety of problems, and in the end, you're not going to be successful. So You should think about this a little more. But for now, let's just say let's focus on dynamic programming, because that's the approach I'm trying to explain to you. But you're right. You should be thinking about divide and conquer. Okay. So one thing that I would suggest is not to worry about the first point and the last point, because we sort of know that we have to go from the westernmost point to the easternmost point and then back. The problem is, what are the other guys that we have to, and by the way, once you decide what's on the eastern path, then the remainder has to be on the western path. So, and also once you decide on which points are on the eastern path, the order becomes fixed, because you can never go this way and then back this way. You can only go in one direction, right? So the order is all fixed. So the only thing that really matters is what goes up and what goes down. And by the way, this is something that may be useful for you to think about. You're never going to have paths that intersect each other. And that's just something that people know. This comes from triangle inequality. Anytime you tell me, if you tell me that this is the best path possible, I'm going to say no way, because I can fix this. I don't even have to know what the right answer is, but I can tell you this is wrong because of something called the triangle inequality. And the way that works is, let's see how I can fix this. Yeah, so what I do is, instead of going directly from here to here, I would try to, so right now I have 3 intersections. I can cut it down to 2 and actually reduce the cost by going through here and then there. So now I have to remove this, which means that this guy will shortcut from here to here. So now I have this way followed by that way, and I can assure you that this new path is better because of something called triangle inequality. By the way, what is triangle inequality?
The sum of 2 sides is greater than a third.
In any triangle, doesn't matter what it looks like, the sum of 2 of the sides is greater than the third, or greater than or equal to. And if I use that, it turns out I can prove to you that my green path is better than the blue path that we started with. And by the way, here we remove that, we remove that, and we remove that. And we added that. Okay, if I replace those 3 x'd ones with the ones marked, it'll be better. Okay. Any thoughts? Are you ready for some clues?
If they never overlap, won't there be like a division between one part of the plane and the other?
That's a good thought, but that's not necessarily true. And yeah, it does feel like it, but it's not true because so there are some points that you can be sure would be on one of the paths, but it doesn't help you in general. Okay. If I had a bunch of points here, okay, should I get it on my western path or the eastern path? We don't know. But if it's on something called the convex hull, then whatever you just said is correct. So anything that's on the outer rim, those points you can be sure will be either in one direction or the other direction. You can be 100% sure of this. But I can set it up in such a way there's only one point you can be sure about, and 99% of the points you have no idea. Okay. Any thoughts? So I'm going to set this up for you so that it'll give you some structure for the way you think. Unless Ricky wants to say something before I give you some clues.
So I remember in the ICDC competition there was a Biotonic problem.
Yeah.
And you can kind of model this as an array of vertices where there's just one peak, or they're all increasing, or they're all decreasing. I don't know if that helps.
That won't help you as far as I know.
No.
Okay.
There's going to be two paths going. If it's undirected, there's always going to be two paths from the starting point.
Yes.
Could you traverse both paths like at the same time, or like in a recursive manner?
So this is why I said once you decide on the upper path, your lower path is fixed. You don't have a choice, because all the remaining guys have to be on the lower path, and they all have to be from right to left. Okay, so yeah.
So I've never done it before, but
Of course.
thinking if you take what the highest peak is from the lowest depth, and you divide that in half, you'll get where the midpoint is. So anything that falls below the midpoint is one path, is one direction, and whatever's above
Yeah.
the midpoint is.
So so you're thinking along the lines of something like divide and conquer, and I want to recommend that you postpone that thought, because we want to focus on this dynamic programming approach. Okay, you had a thought? Yeah.
So what about we use memorization and
Yeah.
see which path leads to the shortest possible path first?
Right, but how do I keep track of paths? I don't even know how to memorize this. What's my table going to look like? That's really what I want to know, right? I don't know are there rows and columns? Is it 3-dimensional table? Is it 14-dimensional table? What is it? I have no idea, right? Because I don't know what those paths look like. So that causes a lot of trouble for us.
So our goal here, the order to choose the leftmost, can we just, like the way you said, only find the path from the leftmost to the rightmost, and then everything else we know?
Yeah, that works, sure. That's one way to approach this. There are many ways to approach this, by the way. I'm going to tell you my way of thinking, but that doesn't mean that's the only way to solve it, sure. And what you're saying is entirely possible. Okay, so I'm going to help to structure your thinking a little bit, and then I'm going to solicit some answers for you. So we know that here's my leftmost point, here's my rightmost point. And I know roughly that that I would have some path that looks like this and another path that looks like this. And we also know that they're not going to intersect, but that's okay. That's not particularly important at this point. Okay, now why did this die? Okay, right. So what I'm going to do is I'm going to try and generalize this problem by drawing a vertical line and saying, let me find the best answer to the left of this. And then slowly I'll move the red line over until I get the best possible tour all the way. Now, how do I describe the left part of this tour? Well, I know that The points are sitting somewhere, right? Let's say that's what my tour looks like, okay? So I can number all of these from left to right. So this would be 1, this would be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22. Okay, I'm just sorting them by x coordinates, and I'm numbering them. So now, if I draw a vertical line here, I'm saying, let me look at the first 12 points, and every point is either going to be on the upper tour or the lower tour, on the way going west or on the way coming back east. Does this help you? And then I'd like to move this forward and include the 13th point here and say, okay, can I add one more point to this? Because that would give me a recurrence relation, right? Because now I'd be adding one more point, and then I'd go to 14, and then I'd go to 15 and 16 and so on. So every point that I add will either go to the upper tour or the lower tour. How am I doing on time? Okay. So now your idea of memoization might have more structure. That's where I'm trying to get at. And maybe it'll help you to think about this problem in a more structured manner. So let's call this point as point I, which is roughly the same as the label I give to the vertical line because it's just on the other side of point I. And in this case, that's I minus 1, that's I minus 2. So if I look at the last thing on the second tour, let me call this as J. So it
So at every I.
yeah.
So that's where we start, right? We start looking at I, and then we keep.
Well, what I'd like to encourage you to think about is what are the subproblems I'm trying to solve? And then maybe also at the same time think about this recurrence relation. So maybe you're thinking about the recurrence relation. I prefer to think in terms of the subproblems that I want to solve, whichever is convenient for you. Because this is a hard enough problem that we don't know where the ideas are going to come from.
The subproblems would be that I would originally be, I guess, 1 or after.
Right, right. So you would start from here. When it's right here, it's easy.
Yeah.
No big deal. There's nothing, there's no path on either above or below. Then when you come to number 2, you know that either that'll be on the lower path or the upper path. We just don't know, right? So there are only 2 choices, but either way the length is the same. Then when you come to 3, that's when things start to get interesting. Should 3 be put along with the path that already has 2, or should I connect it directly to 1 and make it the other path? We don't know. I'll solve those 2 subproblems. Exactly, exactly. That's why I want you to think in terms of those subproblems, right? The recurrence, the recursion, the recursive solution for this problem. So the way you want to think about this is, I have found the best solutions for everything to the left of this vertical line. How do I move forward, right? That's the way you start to think about this recursive, the recursive solutions. Yeah, you were going to say something?
No, I was going to say, going back to that, when we were on 3,
Yeah.
we had to look at taking the previous, which is 2,
Right.
or the one before that.
That's right. So we know that, let me use the other color. We know that 1 was connected to 2. It didn't matter which way, that it's on one of the paths. But when it comes to 3, you had 2 choices. You could either extend this path and keep the other path still empty, or you could connect it there and it would give you those 2 paths.
So now if our vertical line of I
Correct.
was at 3, that means we have to look
Correct.
at 4.
So your vertical line was here, and now you moved it to here.
Yeah.
And one of those 2 you're going to favor. Well, you don't have to make that decision, because remember, we have this memoization that's going on. We can keep track of a whole bunch of other solutions, because we don't know which of those 2 might be better on for points that show up later. And they might influence, even though this one maybe look better than the other one, it's possible that the other one is what is good when you look at all the remaining points. And that's where it starts to become unclear. Okay? So what am I memoizing? Is this a 2-dimensional dynamic programming, or is it 3-dimensional, or is it higher dimensional? What kind of memoization do I need? What's my table going to look like? Why?
Because there's an X and Y.
That is not so convincing. Sorry. You need a better better understanding of why you want 2-dimensional. So you need to describe that subproblem in a clear manner. Okay? Yeah.
So for, let's say, we're looking at the 4th node now.
Yeah. Yeah.
The 4th node, we would have to consider
Right. So let me redraw this in a slightly better way. Maybe move the 3 up so that it's not so clear that this is the obvious one. So let me put the 3 here. So now I could either go this way, right? I could either go this way, or I could go that way.
So I have something, it's not fully complete, but let's
Yeah.
say we're going through each vertices.
Yeah.
In first person, like 1, 2, 3, 4, 5, whatever, up to the end.
Yeah.
And then at point vertex I,
Yeah.
you said we can either choose top or bottom. But
Yeah.
we also need to keep track of the previous point of like let's say the top one.
That's right.
I don't know if you need also the previous one of the bottom one, because then it becomes 3D.
Well, did everyone understand what he was trying to say? You want to repeat that for everyone?
So let's say we're going through from left to right in terms of x coordinates. So we're at a certain position, and we want to find a recursive solution for this. So we also need to keep track of the previous point of the top one, and like it could be like 8 if we're at 11, doesn't matter. And I don't know if you need the previous one of the bottom one as well to keep this sort of state for the DP.
Would it be 10? Like the bottom would be 10?
Yeah.
So the answer to your question is that if you're at position I, your I minus 1 is either going to be in the upper part or the lower part. So one of them is fixed.
What do you mean one of those two?
One of them has to reach I minus 1,
Okay, yeah.
right? Not fixed. I meant that it must reach, it must touch I minus 1. All right, so let me help you formalize this a little bit more. I don't know how we're doing with time, whether we'll be able to finish this problem or not. Yeah, we have another 15 minutes. So here's what I'm going to do. I'm going to write down A of I comma j to be the best or the shortest Bitonic. It won't be a tour. It would be a partial path, right? Bitonic partial path such that well, here we need to know whether I is bigger than j or I is smaller than j. So let's just say I is less than j. Okay. So we want the best, well, no, actually, let's make I to be bigger than j, so because we've been talking in terms of I. So I is bigger than j, so it's the best Bitonic partial path such that we have two partial paths. One going from point 1 all the way to I, and the other going from 1 all the way to j.
So top or bottom?
We have both,
Yeah.
right?
Okay.
But the first one ends at I, the second one ends at j. All right? So we have partial paths. The first one went all the way up to I. The second one, we have to decide where to end it and keep track of this. And we'll make that the second parameter here. We'll call that as j. By the way, here, the second parameter could be larger than the first parameter. We don't know, but we'll allow that also. So we're writing that. So essentially, this is a subproblem and a solution to a subproblem. We're saying this is the best possible partial path. Partial path means these are two paths that haven't been brought together yet at the other end. So they're open paths, shall we say, and it's the best possible so far by including everything until, yeah, so I should add that here, using points 1, 2, 3, all the way up to I. Okay? Yeah, so your question was?
Yeah, I know. The other thing that connect when you wrote the two diagram.
Yeah.
That's why J is in the bottom and it's not 11.
Right, exactly. Because we don't know where 11 is going to be. Maybe 11 is here, maybe it's not.
Yeah, okay.
It all depends on how it's positioned, right? And instead of committing to anything, we'll just say this is the best you can do to get to I and j. And we'll do this for all possible values of j and all possible values of I. In particular, if one of these is n minus 1, so then now think about how you're going to close the loop, how you're going to close the tour. If I do this until n minus 1, right, I would have all these answers. I would have a of n minus 1, 1. I would have a of n minus 1, 2. I would have, sorry, not 1. I would have 2 and 3 and 4. And all the way up to a of n minus 1, n minus 2. I would have all these problems solved, all these subproblems solved. I would have all those answers. And one of these must give me my final answer. And what's the final answer? If this is the best that I want to choose, then I have to connect the two ends back to the last guy, right? So it's going to be plus the weight of the path from n minus 1 to n, and the weight of the path from 2 to n. So or rather, that's the distance between, instead of weight, let me say distance. Okay? So what I'm doing here is, if I decide to go with this option, I have to connect them to the nth guy, and that's how I'll finish the tour. Right? Or if it's this option, what's it going to be? It's going to be distance of n minus 1 with n again, plus the distance of 3 to n. If it's the last one, it's going to be distance of n minus 1n plus distance n minus 2n. We don't know which of these options is going to be best. We'll look at all of these and pick one. Okay? Now, if we write the recurrence in this manner, we end up with something called an order n cubed algorithm. To turn this into an n squared algorithm is a little more work, but for now, let's focus on an easy solution that we can understand. But I need to make sure that, that you're understanding this formulation and this final piece. I still haven't written down a general recurrence, and I'm going to try and do that for you next. Is this sort of making sense?
Can I point to that graph line?
Sure, sure. Yeah, please come.
Just to make sure like that I understand it. Okay. So according to this,
yeah.
We're going from 1 to n minus 1, which is 21. So it's all this path here. And then 1 to j, so 1 to 2. And then plus the distance.
Correct.
Of n minus 1, so 21 to 22.
Correct.
Plus
yeah.
the distance of 2
right.
to n.
So if you if you look at j, if I put this as j, right, then that's what it's going to look like. So we don't know what's on this path, on the first path. We don't know what's on the second path, but we do know that the first one goes all the way up to n minus 1. Well, one of them has to. The other one stopped at j, whatever that j might be. But then we have to connect those two to n, and that's the last piece. So in order to figure out which of these is best, I would have to look at all these answers. So now this also tells me how I can write down a recurrence at any general position I. And we're going to try and write that down next. So let's see how we can write down a of either I plus 1 j, or, yeah, let's go with this. I've solved all those problems before with I. Now I want to solve a of I plus 1 j. that would be, what is this going to look like, you think? So I have already solved ai comma j, ai, well, I've solved problem, I have all of these solved. I have, oops, sorry. I have a of I comma 1, a of I comma 2, all the way up to a of I comma I minus 1. And I also have a of 1 comma I, 2 comma I, all of these are solved. Okay? In order to solve a of I plus 1 comma j, what do I need?
You can go first. We have the subproblem. We're assuming like the top path is I to 1 to I. So we choose some previous I.
Yeah.
We can choose any of them. We look to all from I to 1.
Okay.
And then the distance from that previous vertex to I plus 1.
Okay. So we know we want to add in I plus 1. I plus 1 might go to the upper path or the lower path. Okay. So what we're going to need is the distance from I plus 1, that's the new one we want to add, to whatever is the last guy on the top path, and or whatever is on the last point on the bottom path. We don't know which one. So let's just say it's it may be to I, or it may be to I minus 1, or it may be to some general j. We don't know which one, right? So it could be all the way up to 1. Sorry, up to 2, because one is separate, one is special. Now, we don't know which of these is going to be right, but then to this, we have to add something. What do I have to add? That's the question, right? Because that's just the length of one edge.
So the previous combination?
So we have to patch it with some optimal solution for whatever is to the left of I. So remember, we are now going from I to I plus 1. Right? And I plus 1 could either be put along with this, or I could patch it up directly to 11, or I could patch it up directly to 10. I just don't know where it goes. Each of those gives me one edge. Then, once I patch up that to that vertex, what's my remainder of the path? What does that look like? That's the question. So what I'm going to do now is to erase all of this green stuff, right? Sorry.
Wait, if, let's say you patch I plus 1 with, for example, I minus 3, right?
Yeah.
So do you need to add I minus 3?
Yeah. So now I have to figure out where to patch up this number 13, right? What are the possibilities? There are lots of possibilities, right? We don't know which one. So I am going to either patch up 13 to 12, or to 11, or to 8, or to 10, or to 9, or to 5, and so on and so forth. Let's say I patch it up to 5. What does the rest of the problem look like? What does the rest of the path look like?
From 1 to...
So there's one that goes from 1 to 5. We don't know what it includes, but that's fine.
And then
And the other path contains what?
Is it 1 to 13?
It goes from 1 to 13 is the new one we added.
To I.
1 to I. So it's 1 to 12, right? So that's what I need to write down here. So it's going to be A of, well, let's do the general one because that's what we need to understand. In one of the sides, you're going to have I, of course. Yeah. And in the other one, you're going to have J. Because one path will end at I, the other path will end at J, and you can add this guy to either the bottom path or the top path. Sorry, yeah, no, I think I made a mistake here. What am I doing? Oh, sorry, this is a mistake. I'm so sorry. If I plus 1 gets attached to J, this should be I plus 1 and I, not J. Why? Because I have now connected I plus 1 to J. Let's call that J. Everything else should be on the other path. And so, oh, no. That's not right. That doesn't make any sense. Sorry, I'm so sorry. This should be, no, I had it right. Looks like I had it right. So I'm going to have AI, AJ, but I don't know whether to add it to this or to that. Yeah. Yeah, the way I've written this is actually incorrect. Let me rewrite this part, but so it's going to be Aij plus the smaller of distance. I can either connect I plus 1 to I, or I can connect I plus 1 to J. Yeah, I think this is the right way to say it. Essentially, you're saying you're now adding the I plus first guy. You already have a solution for I comma J. And either you put I plus first on the upper path or the lower path. If it's the upper path, you're going to add a edge from I plus 1 to I. If it's the other path, you're going to add an edge from I plus 1 to J. Okay? So that's the general approach for J. And so you can go from A of I plus 1 J to, you can write down a recurrence for A of I plus 1 J in this manner. Okay? I don't know if this made sense to you. Any questions? I know I'm running out of time, so I should probably stop soon.
Go
Yeah.
So if this is the recurrence formula, then wouldn't it take O(n) squared to fill up?
Yes,
As long as
yes.
constant?
Well, this is for different values of j. So each recurrence is going to take you order of n times, so it'll give you an order n cubed solution. Right? Because you have n squared such things to solve. Each one can take you linear time because you have to try this for all possible values of j.
Then shouldn't be another variable, ij and then k?
Why?
Because if we're just filling up the table, then
Yeah. So I'm going to say yeah, something is not right. If I do this, then I end up with I plus 1i, not I plus 1j. Yeah, I'd have to rethink this and come back. I should go check what I had in my notes. Something is not right, so I'll try and fix it.
What's the issue with that?
He brings up a different question, but the issue that I have is if I add this edge from I plus 1 to j, I don't get I plus 1j, but I actually get I plus 1i. Okay, so this is not really solving that problem, it's solving some other problem. But Ricky brings up a different issue, saying if this is the case, we already get an order n squared solution. So what's the big? It's not really an order n cubed. So somewhere there's some problem, and I'd have to rethink this. And I know I'm way out of time, so I'll try and finish this next time. Okay. But yeah, feel free to go home and think about this and solve the problem before I do.
Thank you.
All right. Thank you. It didn't work.